day. In this video, I will presenting about volumetric analysis. Volumetric analysis is a quantitative chemical method used to determine the concentration of a substance by measuring the volume of another substance that react with it in a known ratio. This technique is commonly known as stoichiometric analysis or titration. There are several types of volumetric analysis, including direct titration, back titration, also acid-base titration curve. So what is volumetric analysis? Volumetric analysis works by allowing a solution of known concentration called the titrate to react with a solution of unknown concentration. Known as the analysis, the reaction continues until the end point is reached, which is usually indicated by a color change from the volume of filter used. The concentration of the analysis can be calculated accurately. Volumetric analysis is widely used in various industries. In the textile industry, it is used to determine the actual concentration of bleaching agents. In the food industry, volumetric analysis is used to measure the amount of salt or sugar in food products. It is also used to determine the concentration of vitamin C and other additives that affect the color of and quality of food. In environmental monitoring, this method is used to measure the acidity and alkalinity of water sample. It also helps detect pollutants such as acid rain and industrial discharge.
On this slide, I will explain direct titration. Direct titration is a quantitative analytical method where a standard solution known as titrant is added directly to the analyzed solution. The titration continues until the endpoint is reached, which is usually indicated by a color change of an indicator. This method is commonly used because it is simple, accurate, and suitable for reactions that occur quickly and completely. In terms of application, direct titration is widely used to determine the concentration of a substance. For example, in acid-base analysis, it is also applied in water quality analysis, such as determining acidity or alkalinity, and in environmental monitoring to measure chemical levels in samples. Overall, direct titration is an important method in analytical chemistry for routine laboratory and industrial analysis. For this slide, I will explain calculation involved in direct titration. A sample of 0.263 gram of soda ash is analyzed by titrating it with 0.1288 molar hydrochloric acid, and the volume of acid used is 38.27 milliliters. First, we calculate the number of moles of HCl using the formula. Moles equal to molarity times volume in liters. This gives us 4.929 times 10 to the power of negative 3 moles of HCl. Based on the balanced chemical equation, 2 moles of HCl react with 1 mole of sodium carbonate. Therefore, the number of moles sodium carbonate is 4.929 times 10 power of negative 3 divided by 2, which equals to 2.465 times 10 to the power of negative 3 moles. Next, we calculate the mass of sodium carbonate by multiplying the number of moles by its molar mass, which is 105.99 grams per mole. This gives a mass of approximately 0.2612 grams. Finally, the percentage of sodium carbonate in the soda ash sample is calculated using mass of sodium carbonate divided by mass of sample multiplied by 100%. The final result shows that the soda ash contains 99.005% sodium carbonate by weight.
Okay, next I will explain about back titration. So back titration is a titration method used to determine the unknown concentration of a substance. So in this method, an excess amount of a standard solution is added to the sample first. So after the reaction is complete, the excess standard solution is then titrated back. So this is why, because this method is called back titration. And then for differential section, this method is used when direct titrations cannot be carried out. So for example, it is suitable for volatile substance or for reactions that occur slowly. So back titration is also used when the equivalence point is difficult to detect or when the equivalence points occurs before the end of point. So in summary, back titration is very useful when direct titration does not give accurate result. Thank you. And then for the slides, I will explain the calculation used to determine the percentage by mass of calcium carbonates in the sample. So first, an excess of nitric acid was added to the calcium carbonates. So 150.0 ml of 0.2105 m nitric acid was added to 1.3415 gram of calcium carbonate. And after the reaction was complete, the excess nitric acid was back titrations using 0.1055 m sodium hydroxides and 75.5 ml of NaOH was required to reach the end of point. Next, we write the balanced chemical equation. So the first equation shows the reactions between calcium carbonate and nitric acid. So the second equation shows the neutralization reactions between nitric acid and sodium hydroxides. Okay, now we calculate the initial number of moles of nitric acid added using the formula. So moles equal molarity times volume in liters. So the moles of nitric acid added is 0.2105 multiplied by 0.150 liters, which gives 0.031575 moles. We determine the mole of excess nitric acid during the back titrations. Okay, so first we calculate the moles of sodium hydroxide used. So the concentration of NaOH is 0.055 molar and the volume used is 75.5 milliliters, which is 0.0755 liters. So the moles of NaOH used is 0.1055 multiplied by 0.0755, which give 0.007965 moles. So since nitric acid and sodium hydroxides react in a 1:1 ratio, the moles of excess nitric acid is also 0.007965 moles. Okay, next we find the moles of nitric acid that actually reacted with calcium carbonate. So we subtract the excess nitric acid from the initial moles added. So 0.031575 minus with 0.007965 give 0.02361 moles of nitric acid reacted. So according to the balance equations, 2 moles of nitric acid react with 1 mole of calcium carbonate. Therefore, the moles of calcium carbonate reacted is 0.02361 divided by 2, which equals to 0.011805 moles. Okay, now we calculate the mass of calcium carbonate reacted by multiplying the moles by its molar mass, which is 100 grams per mole. So the mass of calcium carbonate is 1.1805 grams, and then finally we calculate the percentage by mass of calcium carbonate in the sample. So this is 1.1805 divided by 1.3415, so multiplied by 100%, which give 87.99% by mass. So that is the final answer for this calculation. Thank you. Okay, next I will explain about acid-base titration curve. So the curve help us to understand how the pH change as a tetrate is added to the solutions. So first, initial pH. Initial pH is the pH of the analyzed solutions before any titrate is added. It depends on the strength and concentration of the acid or base being titrate. It switches when the amounts of acid and base are equal in stoichiometric terms. So for a strong acid, strong base titrations, the pH at this point is usually around 7. At the end point. The end point is the stage where the indicator change color. So this change indicates that the titration has reached or is very close to the equivalence point. For the buffer region is the part of the curve where the pH changes gradually even when more titrate is added. This happens due to the presence of conjugate acid-base pair. Fifth, the shapes of the curve. The shapes of the titration curve can be stepped or gradual, depending on whether strong or weak acid and base are involved. Finally, the indicator. An indicator is used to detect the endpoint of the titrations. It's chosen based on a pH range close to the equivalent points. Okay, for this calculation, we are given the mass of sodium carbonate, which is 0.250 grams. So first, we write the balanced chemical equations. So the equation is Na2CO3 plus 2HCl produce 2NaClH2O and CO2. Next, we calculate the moles of sodium carbonate. So 0.250 grams divided by 106 give us 2.36 times 10 to the power of minus 3 mole of sodium carbonate. So for the balance equations, 1 mole of sodium carbonate react with 2 mole of HCl. So the moles of HCl is 4.72 times 10 to the power of minus 3 moles. Then the volume of HCl is used is 48.60 milliliters, which is equal to 0.04860 liters. Finally, we calculate the molarity of HCl. So 4.72 times 10 to the power of minus 3 divided by 0.04860. So this gives us 0.097 molar. Therefore, the molarity of HCl is 0.097 m.
The experiment that was chosen wants to determine the percentage of iron in an iron supplement tablet. Thus, the objective is to measure the amount of iron that an iron supplement tablet contains through the process of redox titration. Step 1. Obtain 2 iron tablets and place them in 2 separate 250 ml beakers. Add about 15 ml of 1.0 mH2SO4 to each beaker and allow the tablets to sit while you prepare your burette. Step 2. Obtain about 80 ml of the standardized KMNO4 solution. Record the exact molarity from the bottle. Set up a burette and fill it to the near top with the KMNO4 solution. Be sure to drain out some solution to fill the tip of the burette with titrant. Read and record the initial level out of the meniscus in the burette to the near 0.01 ml. Step 3. Take one of the beakers that contains an iron tablet. Use a glass stirring rod to break up the tablet. Not all of the broken tablet dissolve. Continue to chop up the tablet until no large pieces remains. Step 4. Obtain an iron ring and attach it to a ring stand. Place your funnel in the ring. Obtain a large filter paper circle. Fold the paper in half and then half again. Peel away one of the 4 sheets to make a cone. Place the cone into the funnel and moisten it with a little deionized water from your wash bottle. Filter the mixture to the paper in the funnel into your clean 125 ml Erlenmeyer flask. Rinse the beaker with a few portions of deionized water and pass this rinsing through the funnel. Finally, pass a few ml of deionized water to the filter paper. Be sure to catch all of the filtrate in the Erlenmeyer flask. Step 5. Titrate the sample with the permanganate solution. As you begin the titration, you will see that you can add permanganate quite rapidly. When the purple liquid enters the solution in the flask, it becomes colorless instantly. As the titration proceeds, however, the added permanganate begins to produce a purple powder which becomes colorless only when the solution is swirled. At this point, slow down the addition of permanganates. Add the titrant drop by drop, swirling between each drop. The goal of the titration is to find the exact volume just needed to react completely with the substance being measured. The perfect titration is when you add 1 drop of titrant to a colorless solution, which then turns a permanent pinkish color, and that does not fade when the flask is swirled. Once you have achieved this, read and record the final level in the burette to the nearest 0.01 ml. Step 6. Pour the contents of the flask into the appropriate waste container. Make sure that there is enough titrant in your burette for the second experiment. Since all of the tablets you are using are made by the same manufacturer, they should contain similar amount of iron 2 sulfate and require similar volume of titrant. Last step, rinse out the flask and repeat step 3 until 6 with the other tablet. Pour any unused KMNO4 solution into the correct waste container. For the first data, you get 0.38 mass of sodium oxalate, 43.5 final burette reading, 100 initial burette reading, 56.5 volume of KMNO4. For data 2, you get 0.32 for mass of sodium oxalate, 3.5 final burette reading, 50 for initial burette reading, and 46.5 for volume of KMNO4. First, we determine the amount of sodium oxalate used. The molar mass of Na2C2O4 is calculated by adding the atomic weights, 2 sodiums, 2 carbons, and 4 oxygens, giving us 134 G per mole. With an average mass of 0.35 G mentioned in our trials, we calculate the number of moles and by dividing the mass by the molar mass. This gives us 0.0026 moles of oxalate ions. Lastly, we find the concentration of our permanganate solution. The average volume of KMNO4 used in the titration was 0.0515 L. Using the formula M equals to N divided V, we divide the 0.00104 moles of KMNO4 by the volume. This results in a calculated molarity of 0.02019 M. Rounding to 2 decimal places for our final result, the concentration of the MNO4 to the power of negative solution is 0.02 M.
So for the next part, which is conclusions. In conclusions, volumetric analysis is an important quantitative method that is used to determine the concentration of unknown solution accurately. Acid-base titration is the most commonly used technique because it is simple, precise, and reliable. The accuracy of this method depends on proper experimental procedures, correct calculations, and the selection of a suitable indicator. Therefore, volumetric analysis plays a vital role in laboratory work, industrial applications, and environmental monitoring.